All right, let's get straight into it. Today, we are cracking open a classic GCSE chemistry question all about electrolysis from an AQA paper. We're going to go through it step by step, and I'll show you not just the right answers, but why they're the right answers, so you can absolutely lock in every single one of those marks. So, here's the game plan. We'll start by looking at the experimental setup. What we're actually dealing with. Then we'll tackle each part of the question in order. The half equation, the role of reactivity, that tricky 4-mark explanation, and finally, how to make the experiment even better. Then we'll wrap it all up by building your essential electrolysis toolkit. First things first, let's set the scene. Question 7 is all about electrolysis, which, is really just a fancy word for using electricity to split up a compound. This is such a fundamental idea in chemistry, so nailing this is absolutely crucial. Okay, so here's the exact diagram they gave in the exam. Let's break it down. You can see the key bits of kit. 2 electrodes, one positive, one negative, and they're dipped into a solution. They're hooked up to a power supply, and, this is really important, we've got test tubes plunked over the electrodes to catch any gas that bubbles off. This is a classic setup. You're going to see it again and again. Let's jump into the first part of the question, 07.1. This is a nice, quick 1-mark task. It's really just designed to check if you get the hang of half equations, which are just a way of showing what's happening at one specific electrode. So the question asks us to complete this half equation for what's happening at the negative electrode. We're starting with an aluminum ion, Al3+, which has a 3+ charge, and we're ending with a neutral aluminum atom, Al. So the puzzle is pretty simple. How many negative electrons do we need to add to completely cancel out that positive charge? And it all comes down to balancing the charge. To cancel out a 3+ charge, you need exactly 3 negative charges. So the answer is 3 electrons. You literally just write a 3 in that gap. The official AQA answer confirms it, a nice straightforward 1-mark win. Now for question 7.2. This one moves away from the equations and more into the principles. It's really testing our understanding of the reactivity series and how that whole concept applies to electrolysis. So the question points out that there are also sodium ions floating around in the solution. Now, since both sodium and aluminum ions are positive, they're both going to be pulled towards that negative electrode. So why do we only get aluminum metal forming and not sodium? What's going on there?
And this is where a really crucial rule of electrolysis comes into play. When you have a choice of positive metal ions at the negative electrode, it's always the less reactive metal that gets produced. Think of it like a race. It takes less energy to turn a less reactive ion back into an atom. Since aluminium is less reactive than sodium, it wins the race to the electrode, while the more reactive sodium just has to stay behind as an ion. And that's it. That's your 1-mark answer, right there.
Okay, now for the big one, the 4-mark explanation. For questions like these, you've got to be super clear and logical, laying out your thinking step by step to get full credit. Let's walk through the exact 4 points the examiners are looking for. This time, our focus shifting over to the positive electrode. The question asks us to explain how oxygen gas is formed, starting from the water molecules in the solution. We need to connect the dots from H2O all the way to O2. This slide lays out the perfect 4-mark answer, and it even shows you all the different phrases the examiners will accept. Let's go through it. First mark, you've got to say that water molecules break down. Simple. Second mark, this process produces hydroxide ions, and you can write that as OH- or just spell out hydroxide ions. Third mark, these hydroxide ions are negative, right? So they get attracted to the positive electrode. And finally, the 4th mark. At the electrode, the hydroxide ions are discharged, which just means they lose their charge, and they form oxygen gas. The examiners also love the word oxidized, which specifically means losing electrons. So you've got options for how you word it, and any of these combinations will get you all 4 marks. All right, next up in 7.4. This question switches gears a bit and focuses on your practical skills. Is asking how you could improve that apparatus we saw at the start to get much more precise results. Remember those test tubes from the diagram? They're fine for seeing that a gas is being made, but they're pretty useless for measuring how much, right? So this is a 2-mark question. It asks for a better piece of equipment and, crucially, why it's better. And here's how you nail both of those marks. For the first mark, the change, swap the test tubes for measuring cylinders. The mark scheme also says you could use inverted burettes or gas syringes, basically anything that measures volume. And for the second mark, the reason, it's so simple. All of those alternatives have a scale on them. A scale lets you measure the volume accurately, which a plain old test tube just can't do. Okay, now for the final part of the question. It's a quick one-mark calculation, and this is all about reading the information that's hidden inside a balanced chemical equation. The question gives us the overall equation and tells us we've made 20 cubic centimeters of hydrogen gas. All we have to do is figure out the volume of oxygen. The secret is right there in the equation. Look at those big numbers in front of the H2 and the O2. That's the mole ratio, and it tells you everything you need to know. And the answer is 10 cubic centimeters. Why? Well, the equation shows a 2 in front of the hydrogen, and there's an invisible 1 in front of the oxygen. That means you get a 2-to-1 ratio. So you will always make half as much oxygen as you do hydrogen. Half of 20 is 10. It's a really easy mark as long as you remember to look at that ratio. All right, we have taken apart every single piece of that question, so let's pull it all together and summarize the key skills we've just used, because these are the exact tools you're going to need for any electrolysis problem they throw at you. And here it is, your essential electrolysis toolkit. To smash these questions, you need to be able to write balanced half equations, you need to apply the reactivity series, and explain what on earth is happening in an aqueous solution. You've got to know which ions go where, suggest practical improvements to an experiment, and use those mole ratios to do simple calculations. Master these key skills, and honestly, you'll be ready for anything. And finally, here's a thought to leave you with. We focused on just one exam question today, but your new toolkit, understanding charge, reactivity, attraction, all of this applies to huge industrial processes that extract the metals that build our entire world. So how might what we've learned today apply on that massive scale? Thanks for joining me for this breakdown.